Okay, I think we'll go ahead and get started on this simulation deep dive. My name is Magnin. I'm a technical marketing manager over here at Autodesk, obviously focusing on Fusion 360. On the line with me as well is Jamie Scherer. He's going to help with questions and if anyone has any issues or things that they need to work through. This is going to be a semi-interactive session. I'm going to actually kind of walk you through some simulation setups, talk about some pitfalls, talk about things to look out for, and we'll actually get you some files to work on. And I don't know if you guys have seen that already, but in the chat window, I've actually sent some messages to some Dropbox links. Those are actually the PowerPoint presentation, and the second document is directions on how to get the files into Fusion 360. So, without further ado, I like to start right on time. It is 10:01. I'm behind schedule already. The agenda for the day is this. I'm not going to, talk about every single thing on this list, but essentially what we're going to be doing here is we're going to be showing you simulation. We're going to talk about the theory. We're going to show you the problem setup. We're going to show you, give you time to work on some self-guided lessons, talk about preferences, and then get into some other more advanced problems. About us, real quick, and I might let Jamie speak to this slide right here, because he is actually on the street team. I'm just kind of helping him out today, because I have a background in simulation. I'll talk about that in just a moment. But Jamie, did you want to talk to this?
Yeah, so again, good morning, good afternoon, everyone. I'm Jamie Scherer. I recognize some names on the list today that have been a part of some of our sessions in the past. A quick overview to the Fusion Street Team, which is, kind of the group that is bringing these, these webinars, these quick start, deep dive trainings to you. Our goal is very simple. We are tasked with connecting with new commercial customers, those of you that are on this call, and helping you. Really, all we want to do is help accelerate your path, your adoption from, whatever you might use today, which, for some of you, you might be new to, design, mechanical engineering, and 3D, etc. Some of you might be coming from tools like SolidWorks or Pro Engineer, Inventor, etc. And what we're here to do through sessions like the one we have today, we've got Aaron, who's going to do a fantastic job of talking about Fusion simulation capabilities. We just want to help, break down any barriers we can and help you guys speed up your adoption, accelerate your adoption in using Fusion. So that's a quick commercial on the street team, Aaron. Back to you.
All right, thank you, sir. You're gonna be up in 2 more slides anyway, so stay close to that speaker. So real quick about me, I'm a mechanical engineer. I went to the University of Nevada, Reno. I'm all over LinkedIn. I'm all over Twitter. If you have questions, comments, anything, feel free to contact me. I love hearing from you guys. In the past, I actually worked as a simulation-specific applications engineer for actually SolidWorks. So I do have some experience using these tools. And that's what I'm going to try to impart on you today. Jamie, I put this slide together for him. I didn't really give him a chance to edit this or choose his picture, but do you want to talk a little bit about yourself?
I do, and you nailed it. So, as Aaron has on there, my background's in industrial design. I went to the Art Institute of Philadelphia for proper education, and after that I spent a number of years in the marine industry. So I was a designer for a yacht company. I've been with Autodesk about 6 years now. Aaron's got me on there. You can find me out in the social channels, LinkedIn, as well as Twitter if you want to say hi. So please reach out and let us know how we can help you with Fusion.
Awesome. Thanks, Jamie. The one thing you didn't talk about is your amazing skills with Photoshop. I really like this picture that you're using on your Twitter account. So wanted to throw that out there. Okay, so real quick about the GoToWebinar interface. I'm sure that everyone in here has already used GoToWebinar or GoToMeeting before, but if you're having audio issues, I'd recommend you either try switching to telephone. You're all muted right now. If you have questions later, we can open it up and actually speak that way, but also you can send in questions. And like I say, Jamie's going to be monitoring that because I'm going to be presenting most of the time. So If you have questions, he'll either ask me or answer them for me. Yeah, just make sure to get those questions in, raise your hand, do whatever you need to do to communicate with us if you're having problems or if you're falling behind. So I always like to kind of wrap out a quick goal of every meeting. I think it helps people understand, what we're trying to accomplish. So in today's meeting, I've already said this, but it's good to just kind of write it down, right? I feel like there's a book that talks about writing down your goals and living your life that way. But today I want to teach you all about theory, problem setup, overcoming common issues and concerns, and just show you how to use these tools to great effect in your designs. So now it's time to get the training files. I actually was playing around with different ways to do this, more efficient ways of doing it, and I don't know if you guys have been using some of our Learn dialogues, our Learn lessons. There's actually open in Fusion buttons, but I wanted to include all of the files in one single button. So this I found was the easiest way to do this. So I'm going to give everyone a little bit of time to do this, but essentially you're going to download those files and I will send them over the comments or the chat section one more time here. Let's see here. There they are. That's going to download like a 20 megabyte basically folder that contains various files that we'll be using during these lessons. Once you've downloaded those, and I'm going to try to follow along with these with you here, so I'm going to just start by clicking the link to download it, and I have two windows up, so you're not actually seeing it download, it's just downloading via Chrome right now. Once it's open, I'm going to jump into Fusion, and I'm going to open up my data panel, and I already have a simulation deep dive project here, so I'm going to create a new project so you guys can see how to do this. And you don't necessarily need to create a new project here. I'm just doing it just to keep these files. I realized I sent that link to Jamie Scherer only rather than all entire audience. There we go. Let's try that again. What I was saying though is you don't necessarily need to create a new project, but these are training files. I don't want them to interfere with, your actual projects that you're working on. So I would recommend you create a new project here, and I'm going to call it Sim Deep Dive. Call it whatever you want. Once it's been created there, I'm going to double click on it. And you got to drop down on that list quite far, and we're going to select this button to import those files. And then from Chrome or wherever your files are, just click and drag and drop those into there and upload those files. So it is a 20 megabyte upload. That's why I wanted to do it before we actually got into the theory. So it's going to actually give you all these files before we get started here. The way I actually encompassed all these different files together is I put them all together in one single design. And then I went into A360 and I exported an F3Z, which contains all the different linked files. So it's just a different way of approaching, sharing files. I didn't want to do like a share link and have you guys have to like get emailed back and all that. Open in Fusion buttons would have been a little more efficient, but I couldn't figure out a way to do it with the F3Z, so that's why we're doing it this way. Anyway, while that's uploading, and I'll keep these steps on the screen. If anyone had problems with that or need help, send in a question, raise your hand, and we can help you out there. And we'll have more time to get into that. But while that's uploading, let's talk a little bit about theory of finite element analysis, is what simulation actually is. So, and again, I sometimes put a lot of text on these slides, but I'm not necessarily going to read every little bit. But what FEA is it's a way to test your designs with real life forces, vibration, heat, and other physical effects. What we're going to learn by using FEA is, whether your design is optimized, whether you can make changes to it to make it perform better, or to make it lighter, to make it dissipate heat more efficiently. So there's quite a lot of details that you can pull out from using an FEA. The great news is that it's really simple to use. I mean, anyone should be able to use finite element analysis in the way that it's presented in Fusion 360. So I hope that everyone's comfortable in approaching this. Inside of Fusion 360 today, we have 4 different study types. Static stress, and that's the one we're going to be focusing on a lot, and that's the one that most people will probably be using. Essentially, it helps you figure out, how your designs react to things like forces and pressures and force displacements and things like that. There's also the ability to do modal frequency studies, so to understand how your bodies might react due to, when there's vibration. There's the ability to do thermal problems, so a lot of electronics and electronics is a really huge area where they're actually using thermal simulations. Obviously, dissipating heat makes those devices run better, last longer, so that's a big concern. And every single day devices are getting smaller and smaller, and so there's more of a struggle to do that efficiently. Connected to thermal problems are thermal stress. So as bodies heat up or cool down at different rates, you can have, pressure building up at interfaces. So if you have 2 different materials essentially heating up, that if there's not areas where they can expand to freely, there's going to be a lot of pressure at their contact, and that can be a big concern for designers. Like I said, though, what I'm going to be talking about for the theory portion, for this first portion, is really related to static stress studies, because it's a good building block. I mean, once you understand how to run a static stress study and you understand the basics behind this type of study, you can use that same approach in most every single other analysis that you end up doing down the line. So keep that in mind. So assumptions for these static stress studies. The material is going to behave linearly, and I'll talk about that in more detail on the next couple slides. Loads are applied slowly and steadily. So if you think about different loading methods, I mean, one could be, just the force that gravity plays on your model, and that would be a very, very slowly applied force. I don't know if you could even really consider it being applied, but the way that the software is going to apply it is very, very slowly. A force, let me use a different example. Gravity wasn't a good example. So if you push on something like a cantilever beam, you put a force on the end of it, and you do it slowly, it's going to behave differently than if you were to apply the same exact force but with an impact. So impact loading is more of a dynamic study, and the mathematics is different. The approach is different, and you'll get very different results if you apply the same force slowly versus if you were to apply it dynamically or with an impact. The other assumption for static stress is that structural deformations are small. Okay, so what do I mean by linear materials? Because if you think about any ductile material like steels, aluminums, their stress strain curve will look something like this, right? So there's this initial rise for the stress strain curve, and then at some point it will hit like a yield point, and the behavior of the material will change at that point. So things will start to stretch and things will start to bend, and it'll actually get stronger at some point before it finally reaches its ultimate strength and fractures. So if you consider this and think about how the software is going to use this information, you're actually using this Young's modulus, which is that rise over run for that first section, to make assumptions on the behavior of that material. Now, that first section, if you continue it on and assume that it will continue to work past that yield point, you're going to get some big errors because the software will assume that this is how the material behaves, So if it gets up here and you're running a problem, your results are not going to be accurate at that point anymore. And I see a question. I'm going to just jump over to my GoToWebinar interface. Yes, the session is being recorded. And yeah, the other question is related to a link to where the deep dive sessions are. I don't know, Jamie, do we provide a link like a...
Yeah, so after the session is over, you guys will all, you can expect a quick survey from me. It'll be about 3 questions. I'll also send out a recording to this session, as well as I can add a link to previous sessions, other deep dive sessions as well.
Okay, cool.
Yep, expect no later than tomorrow.
Awesome. Thank you, sir. Okay, so back on the stress strain curve discussion. Other materials don't behave with that straight linear, initial part of their stress strain curve. Things like elastic materials and plastic materials don't do that. You can see a rubber example presented on this list that also has, aluminum and steels and stuff. So you can, use a linear assumption, like you could do some curve fitting and kind of figure out what a straight line representation might be. So although these materials are not recommended for a linear statics problem that we're going to be showing, I mean, you can still use this information to get some idea of how your model might react. And depending on what curve you're using to fit to that stress strain curve, you could, minimize the error that you might expect. I mean, when I say that you can use it, I would recommend that you use it just to learn about how your model behaves. And I think that's the most powerful way that you can use these tools, these simulation tools and finite element analysis tools is, if you compare 5 different designs, if they're all made of the same material, you can still get an understanding of relatively which one will behave better. I mean, your results might not be empirically correct if you were to run the same analysis like, in the lab. But you're going to be able to learn a lot of information about how your model reacts. So this slide is showing you basically where the finite element part of the finite element analysis name comes from. So the way that it actually breaks down your models and runs the mathematics is it makes tetrahedral elements. So triangular on all sides. At each corner there's nodes, and actually in mid sides there's actually nodes as well, depending on the type of mesh that you're using. But the behavior of these tetrahedral elements is well understood. So using this assumption and kind of breaking down these very complex shapes with these very simple elements, you can that's essentially how these problems are solved, and these are the assumptions that we're using to get this information. So let's actually jump back into Fusion, and hopefully everyone's uploads are completed. And if I close this dialog and refresh this, I hope I put it in the right folder. Okay, I did. It's good to pay attention to that. So this is actually the file that I gave you, but in this file, there's linked files for the original study and the self-guided lessons and the thermal study that we'll be doing later on. So you don't necessarily need this one here. I just kind of threw those all together in this example. So let's open up the first model that we'll be working with. And I'm going to close my data panel at this time. And really right now, I just want to talk about the user interface and kind of show you how to get to the simulation tool and some of the different things you can do once you're there. So by default, this was an imported model, actually, that I added a couple little details to. And I'm not capturing the design history right now. You can tell just by looking at the browser over here. But right now I'm in my sculpt environment, which is not where I need to go to get into my running a simulation on this thing. So what I want to do is I want to use the drop down under sculpt to actually change to my simulation workspace. So I hope everyone knows how to change workspaces. This is where you can go to do different things like render, animate, create your cam toolpaths, etc. Here I'm going to just click on simulation, and you can see I actually do have a study set up here. This is just to, give you something to work with if you get stuck, or if you want to see, different ways of running this. I'm going to collapse that down, and we'll just focus on kind of the interface that we're looking at here, and show you where to go, basically to find different things. So first of all, when you're in the simulation workspace, you'll see your toolbar changes to represent all these very specific commands and options related to simulations. The very first one here is where you can go to begin a new study. So if you click that, you'll see that same list of 4 types of studies that we have access to. I'm going to just cancel this real quick and just continue down the path there, but that's where you go to begin a new simulation study. As indicated, if I just put my cursor there and leave it there, it's going to tell me what each button will do. So you don't necessarily need me to walk you through every single one of these, but if you're unsure of what a button will do, just kind of move your cursor there and let it hang out for a bit. It'll give you this nice tooltip that helps you understand details about what each button will do. So as you can see, the second one will be used to apply study material. So, not necessarily related to the materials that you might use in your design. I mean, you might want to try different materials when you're actually simulating something. So these are your study specific materials. The next one over here is where you'll add structural constraints. So this is how you tie something down to attach it to something. Looking at this bracket that we have, you can see that it's got some threaded pieces there and some counterbores, it looks like. So, that's a good indicator of where this thing might be constrained. There's various types of constraints. I'm not necessarily going to, walk you through every single one that's available to you, but it's something that you guys can explore later and kind of work out to figure out which ones to use. The next one on here is your structural loading, and this is one that I think people, just get right away, because, if you're wanting to run a study, you probably have an idea of, how your model's being loaded. So this is where you'll go to apply those loads. Next one on here is contact. This is how you tell the solver how bodies interact with one another, if they slide on one another's faces, if they're bonded together, etc. And then you get into these other ones, and this will get into display options, and we'll get into those later. This is where you go to solve. This is where you go to re-access your settings. And I'll talk about that. I'll probably access it, a number of times through this presentation. But for now, we'll just keep that as is. And then you get into your results and inspection options at the very end. They're kind of similar to what, the inspect and select options are similar in all different workspaces in Fusion 360. So having this study actually already created in here helps me out here, because as you'll see, I can have multiple studies. So I'm going to just create a new study here, and you don't necessarily need to do this along with me, but I'll create a new static study real quick, and you'll see that it just adds another study to this list. So most all designs will be loaded in various ways. So you will want to create different studies for each load scenario. So you can see that now I have 2 different studies set up, and similar to how you can activate components in a design, you can activate study. So right now I'm active on study 2. I can just tell by the coloration in that browser. If I want to activate finish once again to go back to working on that, I can just select it and click the little toggle there, or I can right click and say activate. Okay, so in each study that you set up, you'll see the ability to do things like include or exclude certain bodies from the analysis. Sometimes you'll have a huge assembly and you really just want to focus on 1, 2, 3, 4 different parts. Here you can go to suppress or unsuppress bodies from the analysis. Here you can also go to hide or show bodies. If you're post-processing and you want to just focus on results for something, you can hide or show bodies from there. Next one is your study materials, and you can see that the material in use is this titanium. To change this, I'll be getting into that later. Then it goes down to constraints, loads, contact, mesh, and finally your results. So when I go to set up a problem, you usually just start from the top and work your way down. And if we look at this new study that we just created, it's presented in the same way. It just doesn't have constraints or loads already set up. So you just start from the top, work your way down. Once you mesh it, you can run it, start to get some results. One thing to pay attention to is this little solve button, which is nice. It tells you, if it's ready to solve, or if, you need to apply some more boundary conditions, or if it needs more information before it can run. Right now, it's giving me the big red no-go signal. So it's telling me this is not ready to run. I really haven't set any details up for this, so I cannot run a study right now. And I believe if I select it, it's going to tell me what's missing. It's missing loads, it's missing constraints. So it's always good to have that feedback. Okay, back to PowerPoint. So problem setup. With every problem that you set up, there's various things that you need to consider. And as you saw, most of them have been presented to you already. So you can see things like materials need to be set up, things like loading conditions need to be considered, things like interface and connection. So that file that you're using is actually from a previous GrabCAD challenge. I thought it was really cool. I think it was GE Aviation or somebody basically threw this part out there into GrabCAD and just said, hey guys, go crazy with this. And they gave prize money to the best designs. But they gave 4 different loading conditions, and they basically said, this thing's going to be created with additive manufacturing. So, constraints related to traditional manufacturing, CNC style designs are now out the window. You can basically do whatever it is that you want. And it was really neat. I just love seeing all the creative designs that people came up with. And so that's kind of where we're going to start this from, and that's where we're going to be building off of. So I've already shown you the original design that they sent out. They figured they could, cut some fat off of it basically, but the setup that we're going to run through for this case, and what I'd recommend that you use for every simulation that you use going forward, is this. Your design part or assembly, whatever it is that you're working on, it's not necessarily the body or geometry that you want to run a simulation on. There are details in there that are not necessary for the simulation, right? So this is important to consider, and this is something that I'd recommend that everyone consider when they go to run their studies. And I'll talk about what that is in just a moment. I'm going to jump back into Fusion and actually start working on this model. So simplify the model or geometry that you're going to be using for the simulation front of the design. Next is material definitions. What is the material that you're working with? Is the material that we're using from our database, is that accurate to what you're actually using? You might have different details. I'm going to close this because I'm getting too many emails. If the details that you see in our database are not consistent with what your vendor is telling you, then you need to create your own, custom materials, which is definitely an option. So that's something that you want to pay a lot of attention to. Then you get into your constraints and loads, sometimes called boundary conditions, and we talked about kind of what those will represent. This next slide that you're seeing here is kind of breaking down in a static study what you'd expect to see in terms of structural constraints, which includes things like fixed, very common one, pinned, if you imagine, be able to slide rotationally, frictionless, or would represent, a face that might be on like a really stiff surface, so it isn't necessarily fixed to it. It might be able to slide on it. So prescribed displacement, which is kind of a load if you think about it, but it needs to be represented in the structural constraint. So that's one way of running one of these studies. You could actually force it your bodies to displace a certain amount, and then actually, figure out details related to that. And then finally, Structural loads include things like force, pressure, moments, and remote forces. So sometimes you want to apply a force, 10 meters away from where your geometry actually is. You don't need to include every detail of every part that applies that load way out there. You can actually just apply that load remotely, which will save you solve time, because the more models you have, the more geometry, the more elements that are in your studies, the longer it's going to take to solve. And the best way to use these tools is to basically try to get through as many calculations as possible. Get through iteration and iteration and iteration, and that way you're going to be able to make your designs as optimized as humanly possible. So back to Fusion. And this was laid out, the actual setup that we're going to be using here is laid out on that PDF that I sent you at the beginning, which included all the slides. So if you want to jump back to that on your own personal screens, you can do so. But let's set this up, and following along with what I mentioned there, let's actually simplify this first. So if I rotate this thing around, and you can see I added a nice GrabCAD to the back. I'm not trying to advertise for them. I was just gonna, needed some text to go on there. But right now I'm in my simulation workspace. So to actually change the model, to get rid of that GrabCAD text on the back and the modeled threads that are in here, I need to change to my modeling workspace. So I'm going to just use the drop down to change from my simulation workspace and jump into model. I got a question here to include the files one more time. Here it is. And I'm just going to send that to the entire audience again. So this is the PowerPoint presentation that I'm using. Okay, so I'm back in my modeling environment. I'm going to double click my mouse wheel to do a zoom to fit. And the very first thing I might want to do is change the orientation of this model. Like I'm really not enjoying how it rotates, and that's just because this thing is imported. This was created from the model that they provided on the GrabCAD website. So what I want to do, and I like to use the rotate, the orbit about, what's it called again? I have the worst memory. The constrained orbit. With the way it is oriented right now, it's making it really hard to kind of rotate and see the back end of this thing. So what I want to do here is I want to just look at this from the top, and I could spend more time and actually get it like normal to that face. I'm not too worried about getting it perfect, so I don't really care too much. But once I get it to look like this, I can jump up to my view cube up here, right click on the little house that you see here, and I could set the current view as my top view or my front view. And in this case, I want this to be my top view because I want it to rotate as if it's, resting on a countertop or something. So I'll set this as my top view. Now I can rotate around and orient this much easier. I really like to use that constraint orbit. It really helps out to kind of see and rotate things. In my personal preference, it's up to you though how you do that. Again, to set those views, right click that top level, that little house from the view cube, and set your current view using the options shown on screen right now. I'm gonna have a quick drink of water. Talking constantly gets a little difficult. All right. So the reason why I brought us back to the modeling workspace is because it has additional details that I don't necessarily want. Now, I actually, added these on purpose so that you could see this and make this a part of the lesson. So I do actually have features over here that I can actually just delete. Otherwise, there's other ways that you can delete details like this. You can use some selection tools and just delete details right out. If I wanted to, I could probably select all the faces here, and I just need to check my selection here and always jump into these selection filters. It's really helpful to get into. But I'm not necessarily worried about doing this too much, but here I might just say body faces, do my selection from left to right to get all those details. And I do want to select through on because it missed all those faces. Let's do that one more time. And you can see it got all those faces. I should be able to just hit my delete key on my keyboard there and get rid of, you know, one of those letters, and I can continue to do all these, but I think everybody gets how amazing our delete options are. And we'll do one more letter. And if it misses some of the selections, you just have to add them. Missed a couple, just I wasn't paying as much attention on this one. Hit delete. So there's a lot of really nice ways of interacting and making changes to imported geometry like this. But as I mentioned, I actually added these on purpose to make this part of the lesson. So I'm going to just delete those features. So I'll delete the GrabCAD text on the back of this. And also the threaded features. I don't need modeled threads in my simulation. Those small faces, those little, you know, helical cuts, you know, make it really difficult to solve in those areas. So it'll add a lot of elements in those areas that aren't necessarily going to add a lot to the details I'm pulling out from the simulation. So we'll just delete those 4 threads out as well. And there we go. We're back to how this model was actually sent. So let's go ahead and change to the simulation workspace again. And we'll begin to set up the study. So I'm going to use the drop down under study here or I'll just select the study, new simulation study button, and I'll select static stress. And you can tell which one's selected. It should have that little faint blue outline there to help indicate, and also the text color will change to indicate that. You'll see there are tooltips related to these to help you understand exactly what these should be used for and what they shouldn't be used for. So make sure to pay attention to those again if you want to learn more. Before I click OK, I do want to expand out the settings here. I just want to show you some additional details that we have here. So first of all, in the general section of this, we can give it a name. So I'll just say, you know, example 1. It's always good to name your items. It's good to name all your details because you can, you know, it helps with the organization down the line. There's a default contact type, and we'll talk more about contact later. In this case, it doesn't really play into it. We'll talk about why that is, but I think you guys all get it. I mean, it's one single body, so there's really not things or, you know, interactions between bodies that you need to consider necessarily. And then contact tolerance, again, that kind of goes along with that same last option there. But in the mesh settings, you can get in and define things like average element size. So if you want to get a really fine result, you can reduce this. The next one is related to the adaptive meshing. We'll talk about that later. Next is turn angle and grading factor. And again, I have slides that cover details of what these mean to you. So we'll not necessarily cover those right now. It's going to be a part of a later lesson. One thing that I might want to do is turn on or off my create curved mesh elements depending on what I'm doing. If it's a first pass analysis like we're doing right now, we just, you know, we want results as fast as possible. So if I were to turn this off, I would get those results much faster because basically it changes the type of element from like a draft quality, if you will. So it'll only have, 4 nodes to like a higher quality first order element, which will have 10 nodes. So just pay attention to that. We'll keep that off for now and we'll revisit that at a later time. The last thing on here is the adaptive mesh refinement options, and this is an amazing tool because when you run these analyses, your first results are not necessarily correct. There's actually a process that you kind of need to go through to figure out and verify that your results are accurate, and this will do it automatically for you. We'll keep it off for now, but again, we'll come back and revisit this at a later time. So we'll click OK. Here's our example 1 study, and the first thing I want to do is I want to just verify, you know, what's in my parts folder. Essentially here it's just showing me there's one single body in here, so not much to do there. The next thing is study material. So I'm going to jump back into PowerPoint, and I probably should have added this slide. at that point in my presentation. But here you can see the material they want us to use is this titanium material. They gave us service temperature, but we're not going to consider that in this first study that we set up. The interface is talking about the pins. That's where the load's actually being applied, and the other interface is where the bolts are actually connecting this thing to the airplane or whatever this thing's actually mounted on. So back in Fusion, let's apply the material. That was the first thing that was on that list. So we'll just right click and select Study Materials. And here you can see, just by default, when I import items, I think it automatically wants to apply steel. If you jump into your actual Fusion preferences, you'll see options to change what it's being brought in as. But in this case, we want to change this study material to be that titanium material that we saw there. So we'll just use that drop down, and we'll start to scroll through. But a quick way to kind of filter through is just to type in T on your keyboard. Looks like teak is the first one that comes up, not necessarily what we're looking for, but if you scroll down a couple more, you'll see this titanium alloy. So we'll select that, and we can consider safety factor, or how it's actually going to calculate the safety factor for us. We'll keep it on yield strength. And if we want to learn about the properties of this, we can expand this out and see what the assumptions are for this material in our database. We'll click OK to that. And now this is this titanium material. We can expand this out and see it's been applied to that model. Now, I like to turn off the display of the material in the simulation workspace. It's up to you how you want to do it. I'll turn it on in this case. I think that actually looks a little bit better. Gives it a little bit of color actually. So I'll turn it on in this case, but the reason why I have it off is that if you go and you start a new study and it's, you haven't paid a lot of attention to the materials that you've been applying in the design, it could look really odd in your simulation if you have this not turned off or shown to include the study material. So just, it's just my personal preference. It's up to you how you handle that though. Okay, so that's set. Next are constraints. So let's right click on my constraints. And again, I'm just working from the top and I'm going down. So I'm going to select to apply a structural constraint. And in this case, I want to fix not only the face where the bolt is going to be threaded, but also the top where the bolt is going to be applied as well. So, and we'll just select the 4 cylindrical faces. And we can do this all in one fell swoop. We'll select the 4 top faces there as well. And you can pay attention to other details here, like, axes and types of constraints. But in this case, we just want to fix those 8 faces and we should be good to go. And the reason why I'm using the top faces as well is I'm considering the bolt head is actually pressing down on that pretty hard and is actually essentially fixing those faces down. So we'll click OK to that. And they didn't really necessarily mention this in the GrabCAD challenge, but on the back face of this, I think you would want to also consider that there's something stiff there that's not necessarily fixing this face, but it's keeping it from, sliding in and out of this plane that it's on. So I'm going to do another constraint here. So I'm going to right click on my constraints and I'm going to select to insert a structural constraint. Don't want to use fixed, so I'm going to move my mouse cursor over here to the dialog box, and I'm going to say, instead of fixed, let's say frictionless. The target will just be selected right from the graphics area. And just like that, you can see how easy it was to apply the constraints for this setup. Now, when I click OK, they will stay visible, so I can actually select this from the graphics area, and as you're using these tools more and more, you'll become familiarized with what the different icons will mean and how they'll be used. So you can fixed is pretty self-explanatory, a nice little lock mechanism. Also the frictionless, I mean, I'm starting to remember what that is, but it takes a little bit of time to just make it automatic essentially. Now, there's a lot of times where I don't want to see those, so I'll just use the same hide shell options that we have in all parts of Fusion 360. Just click the little light bulb there. It's gonna hide those away from us. It doesn't mean that they're not going to be used. Most definitely not. They're still going to be used in the calculation, but they're just not going to show the icons in the graphics area. Now, if I wanted to try this study again without the frictionless, I could do things in here, and I could just suppress or unsuppress things. When things are suppressed, you'll see it has that display there. The checkbox goes away, which essentially is your suppress option. I don't need to right click and select suppress. I'm just old school. But you can also unsuppress it. But you know, this is good to use if you want to try some different, you know, like reuse the same setup, just try different things essentially. So I'm going to turn that back on, and I'll use the toggle this time. And then we'll get into the loads. So we'll rotate it back around. Sometimes it, you know, okay. So my orbiting is different right now, if you'll notice. That's because the different views that you use are specific to that workspace. So sometimes in CAM you want to use a very specific orientation, or sometimes in modeling you want to use a very specific orientation. So I was having difficulty kind of rotating around there to see this a little bit better. So if I wanted to, I could use that same tool I showed you before. Just right click, set current view as top, and then it'll be a little bit easier for me to rotate this thing around. Beautiful. Okay, so back to the PowerPoint. Looks like the first load condition I'm going to try is 8,000 pounds acting directly up from where that pin would be located. So back in Fusion, let's go ahead and do this. And I can use my keyboard shortcuts. I can hit S on my keyboard to open up the ability to add your constraints and forces, etc. I can also right click and hold and use the mouse gesture shortcut to find things like your structural constraints, your loads, your materials, etc. So let's go ahead and just scroll through this and go through structural load. I can just let go of the right mouse button, and there we go. We've turned on our structural load. When we're applying this, you can see there's a nice little option to change types and apply values using this little icon, or I can use the normal dialog box. So we'll apply this 8,000 pounds over these two faces. So I'll just select both of those faces. Using this dialog here, I'll type in a value, but I really need to pay attention to how this is being applied, right? So the default orientation for your loads is normal. With a cylindrical face, normal is basically just outward from the center, right? So that's not accurate. I need it to go directly upward. So this is one thing that I really like about Fusion 360 simulation tool, is that you have this ability to play with how things are applied, and even the area in which the forces are being applied. This limit target helps you kind of focus the forces on a very specific area. In this case, I could use things like angles to try to you know, orient the forces upward, but you'll see that because this model came in at that weird angle, and that's just because that's the way it was imported. I don't know what software they made this in, but it has a very strange orientation. So that's not quite going to do it for me. I could also consider using things like vectors, but again, it's going to fall victim to the same issue that we were having with the other one. It's just this really weird orientation that we have. And the last thing is the option to use reference angle. And it looks like I have a question right now that's a good time for me to address it. It's related to units. Right now, mine's showing in pound force, and that's just because that's a preference that I've set. If yours is not showing in pound force, use this little icon here to override the units. So I could say, instead of using pound force, I can say I want to use newtons, dynes, ounce force, ton force, etc. So if yours is in newtons, go ahead and change this to pound force. Type in that 8,000 pounds once again. And back to where I was at before. Thanks for bringing that to my attention, John. Back to where we were before, we're going to use this reference angle type to define the direction for this. Because this strange orientation that this model's in. So with reference angle set, I can go and I can select a model edge as my reference angle, which is pointing directly upward, which is perfect, right? So we're going to apply that 8,000 pounds to the cylindrical faces that you see there directly upward, and we're going to click OK. Okay, so the next thing that I want to do is basically work my way down, right? So next thing is contacts. I don't need to consider contacts for this model because I had to show you my slide animation because I spent a lot of time doing that. I don't need to consider contacts because there's only one single body in here. So contacts is just a step that we can skip in this case. After that, we're going to go and we're going to mesh this model, which is breaking it down into those finite elements, those tetrahedrons that I showed you earlier, and then we're going to solve it. So jumping back into Fusion, let's just skip past contacts, right click on mesh, and select to either generate the mesh or access the mesh settings. I'm going to access the mesh settings real quick just to show you it took on all those details that I set when we went to define the study from the get-go. So that 10% average element length, 20, I turned off the curved mesh elements. If you want to do that along with me, you can. And we'll click OK, and then we'll solve this guy, or sorry, we'll mesh it first. So I'm going to right click on my mesh icon once again, and I'll select generate mesh. And just like that, you can see it breaks this complex shape down into these, bite-sized chunks that we can or have a good understanding of how they behave under loads or with displacements. Now, it is very boxy looking, right? And that is related to that type of elements. I'm just using the poorer quality elements so that we can solve this extremely fast. And, for a single body analysis like I'm doing right now, I probably wouldn't use this simple mesh style. I'm just doing it to demonstrate what the option will do for you. So at this point, our light is showing green. We're ready to go. Let's go ahead and solve this. You'll see this thing will solve in like 1 second, basically. So fast. It's a really simple model. We're using a simple mesh, and it's not very refined either. So once it solves, we're getting into post-processing this and understanding, what it is that we're looking at. And this is probably one of the most important parts of, a study. This is what it's all for, right? I mean, what we see in this not only will help us understand if we're setting the problem up properly, but it's also going to help us understand if, our design needs to change. So the default plot that shows up now when I've solved this is safety factor. And I can come over here and I can slide this scale around. I can put it wherever I want. If I want it really close to my model, if I'm going to take a screenshot and share it with someone, I can put it really close. To move it, just move your cursor over it until your cursor changes that little hand, and then click and hold. We can access settings for the legend. We can change the size. Right now it's small. We can change it to normal, or we can change it to large as well. We can change color transition from smooth to banded. And this is kind of old school way of looking at your simulation results. Helps you really visualize, the changes from one safety factor to the other in this case. We can also go back to that and change the plot shading as well to help visualize, what we're seeing there, or to make it easier to see. I'm going to actually go with shaded. No, let's go with presentation. That looks a little bit better. Okay, so once, I'm happy with my legend, I can actually come back over here and I can change, what it is that we're seeing. So right now we're showing safety factor, and the location of this is not really good for seeing that value there, but the minimum factor safety is indicated right here. It's 3.62, and for aerospace and for, automotive and things like that, they don't usually shoot for 3 as a safety factor, so this thing's a little bit overbuilt. But again, this is the very first pass analysis. It's not hugely accurate because the elements that I'm using are not refined, and they're not It hasn't, converged, I would say, and we'll talk about what that means in just a moment here. But just keep that in mind. It's 3.62 is the minimum. It's called out there, and I can use this slider to kind of scroll through and see, where areas are above or below certain values. So, for a factor of safety, I probably want to look at, where everything's below, 6 maybe, and you can see it's just these very small areas of this model. So you can filter through and kind of get a good understanding of what's going on with this. The other things that we can look at from our results include stress. You can see the maximums indicated here, minimum as well. We can look at things like displacement. And I'm going to rotate this around and show you, it looks very, very displaced, very deformed in the way that we're looking at it right now. That's just due to the fact that we like to pronounce the displacement so much so that you can understand more about how it's actually displacing. You'll see the actual value that it's displacing right now is, 0.06 millimeters. So pay attention to what's up here as well. You can always change the unit system that we're looking at here. We could say, mil here instead. So this is a very small displacement. If you want to change the scaling that it's using, if you go to your results, you can see the very first thing in here is your deformation scale. So if you want to say, actual displacement, it's not going to show any difference essentially. If you want to help pronounce it even further than what it's being presented as to begin with, you can go up to 5 times. But that doesn't quite help me visualize this. So usually the deformation scale, the adjusted, it uses like an internal algorithm to kind of figure out the best way to displace this and not make it look really odd like it looks right now. So we'll use that adjusted style there. And a good step to go through when you first create a study is to animate it. And that's probably the reason why this animate button is the top level thing in our results folder here. Our results tools, I should say. So if I click that and hit play, it's going to animate it. And it's going to use whatever is currently showing in the simulation results at that moment. So because I'm on a displacement plot, it's showing me the displacement animating. You can change the number of steps. If you want to make it really smooth, you can bump this up to like 40 or something, and you can see it'll do it nice and slow, and you can save out the animation and share that with somebody. You can slow or speed up the results if you want. We'll go to fast. Oh, that looks pretty cool, although the mesh is kind of poor. But so this is a good step to go through on your first setup, because your setups will not be perfect the very first time you go and you run your finite element analysis. Even, figuring out how to set up a problem takes a couple iterations. I might have, constrained it improperly, or I might have applied a load at like too high of a value that it displaces too much. So the very first thing I'd recommend when you actually are setting up your problems for the first time is run the problem, animate the results. If it's not displacing the way that you'd expect, then you probably have set something up wrong. It's not, the issue is probably not related to, the mathematics behind it. It's related to the setup. And I have a slide that kind of speaks to that a little bit in more detail. But let's go ahead and cancel that real quick. Let's change maybe our results here. Let's turn on some additional options here. And I'd recommend that you kind of just get into these options and really dig around. Like, you can create a slicing plane. You can see I can scroll over different faces. It'll start to create the slicing plane. But once I get to the face I actually want, maybe I want to use like this end face, I can slide this through and I can visually see, what's going on through the center of this model in more detail. If I am happy with this slicing plane, I can click OK. It'll keep it open no matter what results I'm looking at: stress, strain, displacement, etc. One thing I need to note in stress, there's a lot of different types of stress that you can consider. Von Mises is the default. There's also your principals, your normals, your shears. Again, you can change your unit systems here. we'll jump through and we'll say, you know, maybe we want to show our min and max. So this will help you visualize where the maximum stress is. And again, this is going to depend on what you're looking at the moment. So minimum is essentially 0, you know, 4.9 e to the -5th. Yeah, that's 0. Your max is, you know, 35 KSI. If we change this to displacement, it's going to show us our max displacement location is somewhere in the tip of that. That makes sense. And minimum will be 0 once again. And then we'll continue on and we'll say, you know, there's other ways of interacting with this. We can create things like surface probes and point probes. So a surface probe, you just can place these, you know, all along the surfaces of this model. So if I want to see how the displacement changes along the edge of this, I can just drop as many of these as I want. And once they've been placed, darn it, I hit escape and I got rid of all those. Once they've been placed, I'll do a couple less this time. You click OK, and then you can move them around. You saw that they were kind of overlapping before. Maybe I want them up on top here. Whatever you need to do, you can just slide them around and get a lot of details as to what's going on here. And as you rotate, it's going to rotate the display there. And again, these will change. You can change it to safety factor, and it'll give you those details instead. So there's also a point probe, and this one's kind of interesting. This will give the ability to actually probe locations that aren't necessarily you know, on the surface of the model. So I just placed it to begin with, but then I can slide this thing around and put it anywhere I want in this body. So I can just slide it over here. You can get a little bit off grid there, and you'll see it's telling me that, you know, there's no result available at that location because I've just slid it too far outside of the model. But you can slide this around and get some details there. And let's see here, what else? Creating reports is extremely easy. You can create HTML reports and different types of reports. We'll just go ahead and preview this real quick. Your reports will include all kinds of details related to, darn it, it's on my other screen here, 1 second. Slide it over. It'll give you all kinds of details related to, you know, the contact tolerances, the mesh refinement options, the actual fixtures and contacts and your loads and every single little detail that you can get into. So really nice way to share your results with others. And, you know, the other way that you could share your results actually is if you were to just create a share link, right? So if I go back to this dialog, and actually it won't let me do it because I'm in my simulation results. That's why I was going to change to modeling environment. But if I go and I create a share link, this will actually include things like your simulation results. And I'll just copy this and I'll send it to all of you guys. You should probably save the model. But yeah, within those that share link, there's also, in addition to the geometry, there's also going to be your simulation results, your CAM results, your animations that you might be creating, etc. I'll just send that out to you, and I will bring it up on my screen as well. So here's what you should be seeing if you're looking at that. When you first open up that share link, it'll look like this. If you want to look at the simulation results, you just change it here to your simulation results and you'll see the different studies that you have set up. So right now it's only showing that finish. I think it just needs to update what I was just creating there. So give it a little time. That share link will work in 10 minutes. It'll update once the server's been done. So okay, so I've been talking for about 1 hour and 4 minutes straight. I need a little break. So let's jump into a self-guided exercise at this point, and I'll definitely be here to help you out and to guide you along these studies. But I've sent along 2 other parts that actually were submissions for this GrabCAD contest. What I'd recommend that you do is you go through and you set up a similar problem. You can test one model or the other. You can also try the different loading conditions. And maybe when we come back from this breaks / self-guided portion of this lesson, we can actually look into which one you thought would have won the contest. So there are 2 different examples there. If you guys are keeners and can get through multiple setups, that would be great. Otherwise, we can just kind of look at the studies and yeah. So I'm gonna stop talking for a moment. I need a little break, but I will be here to answer questions. Go ahead and open those files up in Fusion, in that wherever you use those, you can see self-guided model 7, self-guided model 8. And while you guys are doing that, I'll keep this GrabCAD challenge up. You can also try doing things like this 45 degrees from vertical load condition 3. That's kind of interesting, as well as the torsional style loading condition. So just pay attention to that, and I will resume this in about 10 minutes. So thank you all for joining, and get to work.
Thanks, Aaron, for that. And so for everyone, if you have any questions while we kind of take 10 minutes for some hands-on time, again, feel free to use the Q&A panel. Type in the questions you have. Also, inside of GoToMeeting, if you want to ask a question to Aaron and I, we'll give you a chance to unmute your phones for the next over the next 10 minutes. Just go ahead and use the raise hand function in GoToWebinar, and I'll unmute you. You can ask a question as well. So other than that, good luck with the exercises. That's not how we can help.
Okay, it's been about 10 minutes now. I don't want to spend too much time on break. I hope that everyone was able to get through a study or 2 in that time. They should solve very quickly. The one of those models has really thin walls, so it will take longer to solve, but it should still solve relatively quickly. So hopefully everyone got a chance to run through some of those. I'm back in my PowerPoint because I wanted to cover this last part I kind of glanced over before, just because we were kind of reaching the end of the hour. But the other thing that should be considered a part of your setup or just the process is that once you run a study, you repeat it, and you either make design changes to your model to try to lighten it up. This thing, as you can see, was overbuilt, so that's why they had this challenge to try to lighten this model and save fuel. That's the big thing with airliners these days, fuel efficiency. So let's see how I could repeat this process really quickly. So I'm back in Fusion 360. I'm going to just switch from my modeling environment to my simulation environment one real quickly. And the way that I want to repeat the process in this case is to actually solve it again, but with better quality. So let's do that, and let me show you how to access some options here and also play with some of the result tools as well. So one thing I do want to do right now is I actually just want to hide all the probes. They're kind of in the way for what I want to see. I can also go back to my results and hide the min-max as well. The other thing that I want is I want to get rid of that slicing plane. One thing I could do is I could right click on it and I could hide or show it so that it doesn't have that big kind of orange faint look to it. But the other thing that I could do is if I dig into my results folder, you'll see my slicing plane or planes, and I can just suppress or unsuppress it if I don't want to see it at that moment, but I can still keep it around to access at a later time. Okay, so one thing I could do to change the mesh is right click on mesh and get into mesh settings, but I did want to show you this. The other way that you can get back to your settings, your just general settings for your setup that you did when you started the analysis, is to click this manage button that you see here, these settings that you see here. This reopens that option that we define things like the general mesh settings and the adaptive mesh refinement, etc. So in this case, I want to just change not the mesh itself. I want to come to the adaptive mesh. Well, let me do two things actually. Let's go to the mesh itself and turn on create curved mesh elements, which will increase the quality of the actual elements themselves. And then we'll jump into mesh refinement. And I'm going to move this slider from left from none up to high. So we'll get a very well refined adaptive mesh run. So I'm going to just move my cursor down to OK and click it. And then I'm going to solve it again. You'll notice that once I made those changes, you'll see that it's telling me my mesh is out of date to begin with. And then also in addition to that, and related to that obviously, is that the results are now out of date as well. So let's just solve it again. Just click the button that you see here. It's going to mesh. It's going to solve. In this case, it's actually going to solve a number of times, but it happens so quickly that you don't really see it just because it's a pretty simple model. If you were to do that with that thin-walled version of this design, you would see it chug through a couple iterations and it would actually take some considerable amount of time. Okay, so what that actually did, if we look at this option here that's brand new, you didn't see it before, this is your convergence plot. So the very first time we ran this, if you recall, the factor of safety was 3.62. If I go check that safety factor right now, you'll see that it actually dropped from 3.62 to 3.1. That's not because the load change or anything about the geometry change. It's because the quality of the results changed. And as the result quality went up, the stress was found to go up as well. So as those elements got smaller, it found that there was higher stress in certain areas. So I'm going to just rotate around, and we could do that, hide show max min again to see where that is. It should be in the exact same location. It just should be a little bit more refined in terms of results. I can rotate around. You can see, a number of elements that we have there now. But when I click my convergence plot, what you want to see here is that, it might start at a low value, but it will actually converge on a solution at some point. And so what you want to see when you're looking at a convergence plot is that, it might change from one iteration to the other, but at some point it should even out. And when it begins to even out, that tells you that your results are quality at that point. Okay, so when you're looking at your convergence plot, you can also look at things like displacement. This is another tool that people will use to find convergence, and that's related to a specific scenario. And I'm going to show you this real quick. You don't necessarily need to run this problem along with me. And I don't know why I just did that. I'm going to stay in Fusion. But I've included some other files here. This classic singularity example file is the one I'm going to use right now. I'm going to run an extremely fast study on it and show you some details of what to expect. So change to my simulation. You can see that it's fixed on the top here, and it's loaded with a force on the end there. So I'm going to check my mesh settings. We'll keep it at 10 for now. We'll turn on my adaptive mesh tool, and then I'll solve this. So in this example, and you'll see this one actually chugs through, and that's because it's refining, over and over again. In this example, and if we look at the load here, you can see it's 200 pounds acting on the end of this. If we look at the maximum stress here, it's 13 KSI, it looks like. So for a 200-pound load on this bracket, that might seem high. If we look at our convergence plot, you'll see something that we don't typically like to see. And that's that it doesn't really converge at any point. I mean, this last iteration, you might make an assumption that it did converge, but I think that if you extrapolate it further and refine the mesh further, it'll just continue to rise to basically infinity. And that's what a singularity is, and that's what this name of this part is derived from. In this corner, if I turn on the mesh, you'll see that the mesh kept getting smaller and smaller and smaller, and that just caused the results to go, or the stresses to keep going higher and higher and higher. So the good news is that as you get like one or two elements away from where this singularity is occurring, where the sharp reentrant corner is causing this stress to go off the charts, your results should be accurate. And one way to double check that your results will be accurate in those areas is to double check your displacement. You'll see that the displacement, although it changed from the first to the second iteration, really did converge on a solution. And that's just due to the way that the mathematics are solved. It's just, a matter of what is actually going on in the background there. So this is a case of a singularity. Anytime you have a sharp corner, anytime you have a point load, it will cause a singularity. Anytime you have even a screw edge can cause a singularity. Anytime you have like a really infinitely small area with some amount of force on it, it'll be a singularity. I guarantee it. So when it comes to actually, looking at these results, again, remember that as you move, one element away from this sharp corner, the results should be accurate. Do I expect this thing to fail at this loading that it's at right now? You'll see that the factor of safety is at 0.22, indicating that, yeah, it did yield already. No, it doesn't necessarily mean that this part will yield, but the mathematics of it and what's actually going on there in the background will make it seem that way. So there's things that you can do to get rid of singularities. I wouldn't necessarily, worry about it all that much, to be honest. It's just as long as you know how to deal with it and how to, recognize when it happens, you can do that. But one thing I could do to fix the singularity in this model's case is just put a fillet on that corner. I made it really huge so you guys could see it clearly. But if I jump back into my simulation and resolve this, by getting rid of that sharp corner, we've actually cleared up the singularity. Now you'll see my convergence plot will actually do just that. It will converge rather than diverge. So those adaptive mesh tools are incredibly helpful to help you understand when your results are, quality versus like a first pass analysis. So make sure to use those. They work in, full assemblies, etc. So it's a good thing to use and consider. Back in the PowerPoint. So which one of these do you think fared better? Sorry, I clicked when I rather want when I wanted to keep it showing. The one on the left actually won the whole competition. I don't know if they actually have put it into production, but it's pretty neat. And I think that Autodesk is actually kind of running the same problem, but using some of their generative techniques within and some really neat tools that will actually figure out the design just by your constraints, loads, and your design, your parameters that you're monitoring. So I think the one on the right here, I liked it just because I thought it would solve quicker than the one on the left, and you could get some results and compare them. That one I think got 8th place, but I would recommend that you jump back into the original and start making changes and just have fun with it. It's a really cool problem. I thought it was a nice example to use. Okay, so preferences. This is something I wanted to cover during this presentation. And I'm not talking about your general, Fusion 360 preferences. I'm talking about your simulation-specific preferences. So let's go ahead and use the drop-down here under my name to access these general preferences. But here you'll see that at the bottom, there's simulation-specific preferences. So you'll see that things like forces, I've changed to use pound force automatically. For temperature, I prefer Celsius. For power, I like watt. For angle, I definitely prefer degrees. I don't get radians. I mean, I've been using them my whole life, but I still don't understand them. What else? The other thing that I would recommend in this is to look at some of the There we go. So, sorry, there were some other options. I knew they were there somewhere. I just was not seeing it. I was blind. Here you can see some of the different options that you have in relation to your result displays. So I actually really don't like scientific display. I do like to just, see everything presented. I do like to hide trailing zeros. There are just different options in here that you can access, and I'd recommend that you take a look at them and use them as you wish. Okay, so I think that about does it. go ahead and close out of that. You can change your units from here, by the way. If you just want to edit your default units, you can change it here. What you shouldn't expect is that if you already have 10 studies set up and you're using millimeters and you're using newtons, everything's not going to change within those ones. It will be that way going forward, essentially. So just something to pay attention to. Okay, back into the PowerPoint. Let's see another study, but let's make it a little more complex. So it's going to follow the same setup: simplification if needed, material definition if needed, constraints and loads, contact, mesh, solve, post-process. Back in Fusion, I'm going to open up a different file here. And in this case, it's going to be and we're not going to be using every single one of these files. I just don't have enough time. That first study took longer than I expected. But know that they're there and that you have some details in the PowerPoint to jump into them later. We're probably not going to have time to do the self-guided clamp because I want to show you some other things to do with simulation. But I'm going to open up the pipe wrench. And this is a model that you might have seen before. I've used it for some videos that I've put together. But this is a study that I want to run on this pipe wrench. I just want to see how it behaves and see what I can learn about it. So if I jump into my simulation workspace, the reason why I'm really bringing this up is because it'll enable me to talk about another important aspect of your simulation studies, and that is contact. So again, I do have a couple of studies set up here. There's a finished study. There's one with partial contact and one with contact missing from quite a lot. So I want to show you how to go through, and you'll notice that the color changed, and this is one of those things, why I like to actually have the study materials turned off. I mean, I don't really need to see that that's steel right now. I kind of like having the color display it sometimes, and from my standpoint, I'm actually creating marketing imagery and stuff, so I do like to see the colors, but that might be different from what you guys are doing. Okay, so let's go ahead and begin a new study here. So I'm just going to select the new study button. I'm going to select my static stress, and I can dig into some settings here to dig into different details. So let's jump into my mesh details. I do want to create curved mesh elements. I could reduce this, but I do want this to solve quickly, and we're getting a little more complex here. There's I don't even know, like 10 different components that make this thing up. And we'll jump into my automatic refinement control. We'll keep that at none for now, but as I set up the problem, as I get further along into it, I can turn that on and I can rerun it and check my convergence graph. So we'll click OK to that, and we're pretty happy with this so far. There are some things I might want to do to simplify it. And simplification doesn't always take the shape of actually going to the modeling workspace and deleting faces or deleting details. In this case, I might want to simplify it just within my simulation context. I can actually simplify this thing quite a lot by just getting rid of one of these components. And I was indicating that with my mouse cursor in the graphics area there. But this guy here, I'm not really concerned about this thing failing. Maybe I want to understand the displacement in the arm here, but I don't really care what's happening at the teeth of this thing. So that's a way that I could simplify this model quite a lot. Do I care about these grooves? No, not necessarily. Not really a huge concern for me. Once again, I mean, in this case, I really just want to get rid of this part, essentially. So we'll do that. Let's expand out this folder and see the different bodies that make this up. And, I don't know which part it actually is to begin with, but I can scroll through and click them, and it'll actually highlight in the graphics area as I move my mouse cursor over them. It's a good idea to name your items as well, but if you click it with this expanded out, it'll help me see where that is. So body 5 is the one. I'm going to just clear that out, and we simplified that model a bit. Just removing that is going to save us calculation time. And the less time it takes to solve, the more iterations we'll get through and the more details we'll actually, have. Okay, so that's good. Let's jump into my study materials just to pay attention to this, what it is. It looks like they're all steel in this case. If anyone's used a pipe wrench before, you probably know it's not steel usually. So I can actually go and I can probably change all of these at once to like, some sort of cast iron or something, something interesting. We'll just do cast iron. There we go. So that'll change all 4 of those. The way I selected all 4 of these, by the way, is I just selected one, held shift, and selected the bottom one. I think you can also do things like use your command selection to just select, every other one and change them. Making every single one of these cast iron, might not be accurate, right? I mean, this is just part of this lesson is just, I want to show you how to change all those materials at once, but you can go through and get more details, maybe make the pin a different material, maybe make the other pieces different materials, but I wanted it to be iron. That's what you'd expect from something like this, I think. So there we go. We've set the materials. We've simplified the study by getting rid of one of the bodies. Now we can get into constraints. So we'll just right click on my constraints folder. We'll define a structural constraint. And what I'm representing here is where it's actually, attached to a pipe or something super stiff, right? So I'm going to just fix these faces, and I didn't get rid of the teeth on this side. That would have required some getting into the modeling workspace and actually deleting things, but I can go through and I can select a number of these just to define this constraint real quick. And you don't necessarily need to pick as many teeth as I did. I'm just trying to imagine it grabbing onto something very stiff. And again, this lesson's really not about the results that we're going to be looking at. It's more about the setup. So just keep that in mind. The last thing is the load. And I want to show you something really cool about the load definitions. I showed you a little bit about the neat loading options that we had, but let's see this again in some more detail. So we'll apply a structural load, we'll apply a force, and then I'll just select a face to start to define the target. So this face makes the most sense for me in looking at this model and understanding how a pipe wrench works. When you select a face like that, it by default wants to get every bit of the face. Now, I could go and I can jump into the modeling workspace and I could actually define a sketch to then do a split to just, to focus on a very particular area of this model. But you don't need to do that in Fusion 360. So split face would enable me to break that face in two in order to just apply the force on the back end of it. So I don't need to do that. What I can do in Fusion 360 with my loading is I can select that face, and then I can use this option right here to limit the target. It is going to limit the target in a circular fashion, but it's going to be really cool, just really easy to apply this load. So let's apply a force. We'll say 200 pounds once again, just imagining something very strong is pushing on this. And I can increase or decrease the area in which this force will be applied. I'm just imagining, like a normal person's hand might be about yay big. And then I can also just click and drag to move this, to put it in a different area, to focus on a different portion of this area, of this model. So I'll just drop it right there. That looks about right. And, forces aren't ever really applied directly on, right? So let's do something else here. Let's go and we can change something to apply different angles to define this load. So I really like using this option as well. You can just, apply it at a small angle in one way, or maybe apply it at another angle in a different way. Just really easily, really quickly, we can really define and control how this load's being applied. So let's go ahead and click OK to that. It is being applied in the correct direction. It is being applied in a particular area of that face that we have. And then we get into the real main guts of this portion of the lesson, which is contact. Now, when you go and you set up your first study or set up your studies, there's this contact tolerance. And what this will do is it'll enable the software to overcome, small gaps in your part to apply contact. So a lot of times when you're designing something like this, the pin isn't exactly the same size as the hole in which it's in, right? There's a tolerance built in there, or at least there should be, or else it's not going to slide very freely. So using this contact tolerance, we can actually overcome those small gaps that you've built into your study. We can also do things like change the default contact type. Now I'm going to keep it bonded in this case, and I'm also going to maybe decrease this tolerance to even lower level, and I'll click OK to that. So bonded isn't really the most accurate way to do this, right? Because you do want things to slide in some cases, but by using bonded, it's going to solve faster because there's less of calculation, intensive calculations that happen. But let's see how to apply contact manually as well. So I'm going to do something here before I start to even define any contact. I'm going to turn on my degree of freedom view. So this is showing me which parts have been fully fixed, which parts are not fully fixed, and which parts are completely free. So the two parts or components that we have in here that have fixtures applied to them, this guy as well as this guy, have some amount of fixed, are fixed to some extent. So it's good to know, good to see, good to understand and dig through and understand what this degree of freedom plot will represent for us. The ones that are red are basically, there's no fixtures or constraints applied to them, and there's no contact connecting them to other parts that might be constrained. So these three parts, you know, this circular piece that you see here, this guy, and the pin, if I were to run a study, they could just fly off the screen, and you know, it basically just wouldn't be too happy with my setup. So let's apply some contact, and let's do it manually to begin with, although the automatic will usually do quite a lot for you. So let's go ahead and just come up to my contact. And if I use the drop down there, you can see different contact types that you can jump into from the get-go to understand what each contact might do for you. Again, look at the tooltips, read the details. There's help information that you can get into to understand exactly when and where to use certain items. But in this case, like I say, I want to use bonded just to get through the study quickly. I also want to do this manually. So I'm going to just select the top level here. And, you know, it is asking me, you know, do you want to save yourself some trouble and automatically create those? I'm going to say no in this case, but in most cases, when you're actually solving problems for yourself, you'll probably say yes to that. What I want to do here is I want to define a bonded contact between two parts here. So let's say, you know, the two parts I want to do are going to be the pin and maybe this guy right here. So what it's looking for me to do is just select two components. And I love this display. It actually hides all the other components that you're not necessarily concerned with. If I zoom in here, you'll notice that the pin, even though I'm creating a contact with it, has gone transparent because it's looking for a target face from the first body, from the orange body that you see in the graphics area right now. So I can click that face, and by default it changes so I can actually see the pin now and has made the other piece transparent. So I can rotate around and I can select this face as the face that I want to create that bonded contact between. So just like that, I was able to create this contact, which is actually quite a hassle if you think about it otherwise, because you know the nature of contacts is that those faces are touching. So by default, they're going to be very difficult to select. This manual contact procedure that we have in Fusion 360 is something that I absolutely love, and I'll do it again here. I'll just select the two components, select the two faces, and okay it. You know, you can jump into recreating or adding more manual contacts just by right-clicking and using your mouse tools there to get into your repeat manual contact. But just like that, we've added some contact. And if I zoom out and look at the degree of freedom plot, nothing's changed. The reason for that is that those two bodies are not connected to the other bodies that are actually fixed. So let's do something here to save me some time. Let's right-click on contacts and do automatic contacts. And I can keep my degree of freedom plot visible as I do this, which helps me really visualize, you know, what's missing, what contacts, you know, I need to pay more attention to. But just like that, the automatic contacts, even with the especially using the tolerance, I should say, has potentially fixed everything in this model. So that's exactly what we want to see. If I expand out the contacts folder now, we'll close this. It was just taking a long time because there are quite a lot. you'll see that it created, it looks like, 41 different contacts. And sometimes the automatic doesn't do a great job of capturing, true details that you want to include in the study. So if you do find that it creates contacts you don't want, you can always, suppress or get rid of those from the study's context. Okay, so I think I'm happy with that. My solve icon's green. I can go ahead and just solve this. So I'll click the solve button and we'll get some results pretty quickly here. Now, I'm willing to guess there's going to be some singularities in this. I mean, just when you have an assembly with, pin edges and sharp edges like this, we could expect to see some amount of singularity, which I would expect is the case, because with a 200-pound force, the minimum safety factor should not be 0.1. What you'd expect when you have a singularity like this is that as you scroll this up, or where it's really visible is in stress, you'll see that it's 99% at 0 on this scale, because the scale is off the charts. But if you scroll this down, you'll get into like the details that are actually going to help you. And well, in this case, there's a really bad singularity, so it's not really giving me quite the amount of detail I want. But as I mentioned at the beginning of this, I wanted to actually look at the displacement in this model. So that's incorrect. 193. So and I could start to get a guess that it wasn't constrained properly, just by the outlined part that's there. That's showing me kind of the undeformed shape in the graphics area there. So what happened there, right? Let's do something here. Let's animate it, and you'll see that, again, this is that step that you should go through when you're first looking at your results. It's sliding in one direction, sliding in the Z direction. So what I'm willing to bet, and that's why it showed as partially fixed in the degree of freedom plot, is that my constraint, I selected the wrong type. So it's just sliding. And that's why you see this crazy value of 193 inches. So let's change this, and that could also play into the values that you were seeing on the stress plot and degree of freedom plot. But let's edit the structural constraint. Let's change that from frictionless to fixed, and we'll click OK. So good thing to pay attention to is the type of constraint that you're using. So we'll solve that real quick. And like I say, this is, missing one small detail in the setup, like the type of constraint, can completely derail your results. That's why it's important to look at your results, animate them. And again, it is a bit of an iterative process, just the setup of your finite element analysis. So there we go. That's more what I'd expect with a 200-pound load on a cast iron pipe wrench. We can look at our stress, and we can look at our safety factor as well, and we can get a better understanding of how this thing performs. So that's more along the lines we'd expect. Again, I would think that there's probably some singularity acting on this somewhere. So it's up to me to go and post-process this and really dig in and try to figure out what's going on there. Okay, so adding custom materials is an important skill to have. When you're in this material browser, make sure that you click the Add New button, kind of hidden down there in the lower left-hand corner. Fill out any details that you see there. But the really important thing is that if you want to use this in a simulations context, you have to hit that little plus sign that you see right there. And I've called it out in the slide to really draw your attention to it. When you add that, it adds other physical parameters to the material, things like your elastic modulus, things like the density, things that play into the actual calculations that you're doing. If it was a thermal problem, you'd have to consider conduction and specific heat and things like that. So click that plus sign. It'll give you the ability to add those additional details. If you need to find custom materials, There's quite a lot of resources on the internet that you can access. MapWeb is a really popular one. There's military spec sheets that I think are very popular as well. I put every spec here. The military provides spec sheets whenever they like bid out a job, and everyone should use the same assumptions for that. That's where they get this, and that's why they have done all this testing for us. And then there's also vendors and different things that you can access that might have details. Use your degree of freedom plot. It's going to help you understand where context might be missing or where other details need to be, other attention needs to be paid. Context is probably the area where I make the most mistakes, although I demonstrated mistakes with a different side of the software. But using the degree of freedom plot and the manual contact creation and the contact tolerance, you can build up some really complex models in a very short amount of time. Getting into mesh settings, I wanted to call out a couple of these. I kind of glanced over them before because I knew these slides were coming up. If you want to just refine the mesh manually rather than using the adaptive tool, you just use this top level one and you reduce it basically. So as you get into lower levels, it's obviously going to take longer to solve, but your results will be better because of it. The second one, they recommend 10 to 20%, but use it with adaptive. The next one, the maximum turn angle, and I didn't really know what this was until I actually put this slide together, but I did it a little while ago. But I think by default it's set at 60, but what it's actually playing with is whenever you have curvature in your model, like on this fillet or in this cylindrical face or this cylindrical face, it plays with how quickly or how slowly it's going to adjust those elements in those areas. So you can see the very extreme scenario of using a 1 degree turn angle will get you some crazy amount of elements in those areas, whereas 15 will be, less refined, but 60 should do in most cases, I think. The grading factor plays with how fast or slow your elements will grow or shrink. So in this case, the one on the left is set as close to 1 as possible as I could get. I think it was like 1.001. I don't know if it actually let me do 1, but by using a grading factor of 1, it basically means that the same elements will be used throughout the same model. The same element size will be used throughout all of the geometry. 1.5 is the recommended, so it's a gradual transition, a very gradual transition. I think that's what you want to see when you're running a simulation or creating the mesh. 10x will adjust the elements extremely fast, and you'll get some weird looking elements. And you typically don't want to see elements like this, these long, elongated, like just oddly shaped elements. I mean, the perfect element would have the same size, edges on every single side of the tetrahedron, so that's important to consider. The curved mesh elements, and I've demonstrated this both visually and speaking about it, but essentially it changes the quality of the elements. So these two items have the same number of elements, but different number of nodes, and the nodes are in the corners and mid sides of each one of these tetrahedrons that you're dealing with. So you can see the differences of having it off and on. The off is good for real quick analyses. The on's good for higher quality stuff. And this one is really handy, and I should have actually used it when I was doing the analysis with the pipe wrench, but using part-based measure for assembly meshes. So if you have 15 parts and one's tiny and one's massive, you don't want them to necessarily have the same general size elements, right? You want it to adjust. So by turning this on, you'll see this very small component in this dumbed down example. It helps you visualize, what that will actually do. So use part-based mesh. Highly recommend that for any time you're running an analysis on an assembly. I did actually show this already. Use A360 to view your data in a web browser. It's pretty neat. It's a great way to share your results. If you don't prefer that, you can use the report generation. It also works as well. And we are not going to have enough time to get through a thermal problem. Maybe I can run a frequency problem, but this was a problem that I wanted to get through, but I just did not manage my time well enough. I did talk about this at the end of this presentation. I just wanted to round out, common problems and concerns that people have when they're running these. Convergence is what you want to see. You will only see the convergence plot when you actually use the adaptive meshing tools. This is your ideal situation that you see here. It gradually kind of tops out. That last value that you see there, the fourth solution step, should be your results that you actually use. Divergence can look like this. It can also take the shape of that, singularity case where it just continues to rise to infinity as those elements get smaller and smaller. This is an important one if you're running any frequency studies. And I'll do this real quick and I'll just show you how easy it is to run a frequency study. So we'll jump into my data panel and I'm going to open up this ship propeller. I thought it was kind of neat, but frequency studies are about as easy as you can get because you don't need to set up constraints. You don't need to set up loads. You can actually just look at the natural frequency of your geometry and it'll just use the material basically in the shapes, right? So I'm going to create a new study here. We'll do a modal frequency. We can look at the settings here. They'll be slightly different. One thing you might want to pay attention to is the number of modes that you're calculating. Usually the first couple are the ones that you're most concerned with, but we'll look at that in just a moment here. We'll click OK. This thing's ready to run. I don't have to do anything else. Let's go ahead and just solve this real quick, and I'll talk about that problem that I was demonstrating in that slide. So it's meshing, it's going to solve, and when we get into this, we'll start to animate these results, and we'll talk about why it's this way. And it's taking a little bit longer than I would like, but we still have 5 minutes. So there, it's solved, and you'll see that the very first mode shape it's giving us is, well, not doing anything. Nor is the second, nor is the third, and nor is the fifth up to the sixth. This might look like it's actually giving you some details, but you can see 0 hertz. That's really not telling you much. So what this is actually doing is related to how it solves. And if you think about it, everything in space really has 3 translational degrees of freedom. So it could slide in the X, Y, or Z direction, or it can rotate about those same axes. So there's 6 degrees of freedom. If you have a study like this, a frequency study that you haven't constrained, each one of these modes that you see will just basically be sliding and rotating about those main degrees of freedom. So they're sliding about the X direction. We'll get into one of the rotational ones and we'll animate it. And you'll see this is just, rotating about the X axis in this case. So basically the results up to that point are, no help to me whatsoever. But as we get into mode 7, mode 8, mode 9, we can animate these and get a really good detail about, the natural frequency for something like this. And you can see this thing's doing some very different things and translating and rotating. So something to pay attention to. There's other result options available with your frequency studies. Your mass participation factor is really important for your different studies. You want to get that up to a higher level than 0, obviously. And the way that you'd probably do that is actually calculate more modes and get more details as the different mode shapes you're going to get into. Okay, so back into PowerPoint. Those are the 6 degrees of freedom. So if you're running a problem and your results are wrong and you just know it, check your setup. And I'm capitalizing this. I'm not yelling at you. I am just trying to emphasize this. There's very few times that the problem is related to the mathematics. 90% of the time, I'll say, probably even higher than that, there's something wrong with your setup. Could be your contacts, could be your loads, could be your constraints, could be your mesh is not fine enough to capture the details that you're after. So something to pay attention to. But at the end of the day, you also need to consider that this is a numerical technique that has simplification, it has rounding errors, it has other things to consider. So if you're even within 5 or even 10% of what you're empirically expecting, that's pretty good. Like I say though, in my experience, the people who get the most out of these tools are the ones that are not trying to recreate empirical data. They're the ones that are actually using this to change their designs to make better designs. So from here, I did want to highlight some upcoming functionality real quickly. CloudSolve is something I'm extremely excited about in this study. There we go. I just want to show you, it's a video. So if you hit solve, you'll be able to solve locally. You'll be able to solve on the cloud as well. Here I'm sending 4 different studies to the cloud. While it's sent those, I can go and I can clone studies. I can recreate new studies. I can apply different materials, and I can solve locally even while I'm waiting for those cloud results to come in. So that solved very quickly, you'll see. It's because it's a really simple problem. I would imagine CloudSolve is going to be much more important for your complex problems as you get your meshes finer and finer. So really exciting development. Here's some Fusion 360 support, and I just pulled this from a slide that was included to me from the street team. It gives you some details on how to contact different people. I would always recommend you go on the forum and fire out your question there, because usually there's other users that could benefit from seeing, what you might be struggling with, or what might be wrong in the software. I mean, there are bugs on occasion. We don't like to admit that, but it happens. But by you communicating that to us and the community, we can fix them, right? So here's some support information, and I think that just about does it. It's at 2 hours. I'm going to go ahead and stop and open up for questions. I think that Jamie's done a great job of handling those so far. Jamie, did you have anything that you wanted to add, or are you still awake?
I'm here. I'm wide awake. I'll say thanks, Aaron, for the deep dive into simulation. This has been fantastic. We even have some requests for a session, maybe more specific on thermal. But I guess we'll just hold it open for a minute and see if anyone has any specific questions. Otherwise, I'll repeat again, everyone, you can expect an email from me in the next day or so that'll have a link to the recording, as well as a short survey. If you could give us some feedback on how we can better provide sessions like this in the future. But again, Aaron, thanks again for the time. I think it was a fantastic overview.
Thank you, sir. All right, we'll hang out for a couple minutes, but otherwise, everyone, I want to wish you all a great day, and fire your questions if you got them. All right, see ya.